I wanted to address a question after class about this problem, problem number 3 in section 13.3. It says to find the length of a curve in an intersection of a cylinder and a plane. So we didn't go over this in class, but there's some information in your book. Let me pull out the book. This is on page 842, I think, in your book, where you have an intersection of a cylinder and a plane, and then you're asked to find the equation, or a vector function in this case. So I think if you're able to find a vector function, then you should be all good. So the process of doing this is to first note that you're dealing with a circle on the XY plane, and then your Z is simply going to be based on the plane. So if you look at the process here, they basically say you're going to let your x equal a circle, sine and cosine, and then your z is equal to 2 minus y if you look at that plane, and then you just replace your y value with the y component of your parametric equation. So let's see if we could do this using the graphing calculator. Let's first take a look at the cylinder. 4x squared plus y squared is equal to 4. And if I were to just to punch that in the graphing calculator, it's going to give me an ellipse, because if I divide by 4, it is exactly an ellipse. But this is supposed to be a cylinder in 3 dimensions, and the thing is that you won't see the 3 dimensions until you draw another graph in 3D. So say you copied this equation, and then you also drew a graph in 3D. In this case, we're going to draw this plane x plus y plus z is equal to 5. And then that ellipse now, that was flat in 2 dimensions, has now become a cylinder. So this is actually the graph that we should be looking at. And at first glance, let's see, it looks like these things don't intersect, but you know, you have to zoom in a nice window to see the actual intersection. So for now, if I just zoom out, oops, the other way, zoom in or zoom out, and then I'll just see that intersection happening over here. It's kind of still difficult to see, so let me actually manually adjust my Z. I know this is above the Z axis, or the XY plane, so I'm just going to go from 0 to 8, and then I'll change this from -4 to 4, and X and Y's will be -4 to 4. So that's a better view of my two surfaces that are intersecting. Now, what I'm interested in seeing is, what I'm interested in doing is to try to find an equation of a parametric curve that follows this path. And so what I'll start with is I'm going to see if I can attempt to draw a parametric curve in 2 dimensions that would mimic this ellipse. And then after I get the x and y components, I would solve for z here and then put in the x and y components, and then that will be my z component. So let's see how this is going to work. I'm going to want a 2D parametric curve that has sine and cosine, and I can just make it go all around 0 to 2 pi. I see that this is not exactly the same as my ellipse, and so we talked about making an ellipse from polar coordinates and then making it into parametric equations, but there's another nice easy trick to make the ellipse happen here. And I see my y getting stretched out to 2 units. So if I just take my y value over here and multiply it or scale it by 2, not 4, then I actually have that ellipse. So let's hide this blue vector or blue graph, and I see my red graph. I'll put that blue graph back on, and then I see that graph. So I see now that this is my parametric equations for 2 dimensions. Now I want to create a 3-dimensional curve where my first 2 dimensions, my x and y, are the same as my x and y as in this curve. But now my t, I'm going to want my t, or my z, I'm sorry, my z, I'm going to want my z to be on this plane. So what I might be interested in doing is solving for this plane, solving for the plane, get the plane by itself, where I get z is equal to 5 minus x minus y, or 5 minus parentheses x plus y. And so if I replace the z with that, except instead of x I'm going to use cosine t, and instead of y I'm going to use 2 sine t, then I should have that curve that I'm looking for. It might be hard to see. Let's see if I can adjust the radius of that curve. Oh, we also want to make sure that this goes all the way from 0 to 2 pi. Okay, there we go. Maybe the radius is a little too big there. There, that should be good enough. That's a good enough view, and we could see that on the xy plane we see that ellipse, and looking at it from any other angle we see that it is in fact the intersection. So if we take the cylinder and the plane out, this is what we see, and if we put the plane back on, we'll see that this is exactly on the plane as expected, and when we put the cylinder back on, you see that this is actually also on the cylinder as expected. So this is your parametric equation that you'll use. Your r of t is equal to cosine t, 2 sine t, and then 5 minus the cosine plus 2 sine t inside. And you went, or we went, from 0 to 2 pi. So that should be enough information for you to use the formula for the arc length. And so you're essentially going to be taking the arc length of this velocity vector from 0 to 2 pi to figure out, and then you just put this into the formula and punch it in the calculator, and then you get your approximation. Okay, so I hope that helps.